A precision ball can carry the correct material name and still fail inside a corrosion-sensitive assembly. In a valve or compact pump, fluid retained against a seat may create a tighter, more aggressive crevice than the surrounding system. Cleaning cycles can concentrate chemicals, repeated drying can leave deposits, and surface damage can initiate corrosion or wear. Choosing among 316, 316L, and 316 LVM therefore requires more than comparing catalog labels. Type 316 is commonly considered where resistance to pitting and crevice corrosion is important, particularly in chloride-containing or chemically demanding environments. Its molybdenum content is relevant, but service performance also depends on temperature, oxygen availability, deposits, surface condition, manufacturing effects, and assembly geometry. The lower carbon designation of 316L may be appropriate when processing, joining, or corrosion-related requirements make that distinction relevant. But the letter alone does not establish superiority. The exact designation and chemistry range must be confirmed in supporting documentation and connected to the proposed manufacturing route and operating environment. 316 LVM calls for a deeper evidence review. Buyers may need defined information on chemistry, vacuum melting claims, inclusion control, surface requirements, cleanliness, processing, and traceability. The designation does not automatically establish implant suitability. Human contact and implant claims depend on the finished component, contact conditions, manufacturing controls, applicable requirements, and the complete validation pathway. A practical selection process starts by assigning application risk. A low-risk case is a dry, controlled mechanism without aggressive media, where dimensional confirmation and a material declaration may be sufficient. Medium risk includes intermittent fluid contact or routine cleaning and calls for lot records, surface control, and sample review. High risk covers recurring chloride or chemical exposure, elevated temperatures, retained deposits, or tight crevices, requiring environment-specific testing or engineering assessment. Critical risk includes safety-sensitive service, uncertain exposure, long-term human contact claims, or regulated conditions that demand application-specific validation and quality evidence. The exposure profile should identify fluid composition, chloride concentration, cleaning chemicals, temperature, residence time, pressure, and wet-dry cycling. It should also establish whether the ball remains immersed, is intermittently wetted, or sits against a seat where liquid can be trapped. Broad labels such as industrial, marine, chemical, or medical do not provide enough detail for material approval. Mechanical and geometric demands remain equally important. Load, speed, contact stress, dimensional grade, surface finish, magnetism, wear, and compatibility with the seat material can determine whether the ball functions correctly. Corrosion resistance cannot compensate for inadequate form control, unsuitable surface condition, or excessive wear. Pits, scratches, embedded contamination, roughness, cleaning residues, protective oils, and packaging materials must all be considered. Before approval, apply 6 evidence checks. Confirm the exact material designation on the quotation and purchase order. Obtain lot-linked chemistry and material records. Define diameter, grade, surface, and packaging criteria. Review the real fluid, cleaning, and temperature conditions. Approve a representative sample through functional testing. Then preserve receiving, inspection, and non-conformance records for traceability. Sample approval should test the supplier's evidence system as well as the component. Documentation must arrive with the lot. Labels must preserve identity through receiving. Stated characteristics must be measurable, and technical answers must remain consistent with the original claim. Finally, define when reapproval is required. A change in material source, melting route claim, dimensions, ball grade, surface treatment, cleaning method, packaging, or process medium can alter corrosion and functional performance. The defensible choice is not the designation that sounds most advanced. It is the one supported by evidence proportionate to the assembly's actual risk.